Just to set this up, I want to talk a little bit while I'm looking at the title slide about just the nature of our industry, and in particular the demographics of our industry, which, demographics is a word that I think has been used in both the keynote presentations at this conference so far, the one yesterday about training new people and experienced people, helping to grow younger people in the industry, and also, of course, this morning in the much more kind of straight up diversity focused talk. But there's another aspect of diversity that probably very directly affects a good proportion of the people at particularly this conference, which is to do with age, right? I'm 47, right? And I haven't done the statistics for a few years, but that puts me in like the top 3% of the age distribution of programmers in the world, right? I don't think 47 is very old, really. When I go and see my doctor to have my blood pressure taken, she says, "You're still a young man." But I'm in the top 3% of the bracket. And the reason I'm in the top 3%, or the reason young people like me, or at least middle-aged people like me, are in a tiny fraction of the top part of the age distribution, is because there is such an enormous number of people at the bottom end of the age distribution. And that is a reflection of something we've all become very familiar with in the last few years, which is the nature of exponential growth. And whenever you have a system where exponential growth is happening, it doesn't matter what it is, whether it's viruses or developers in our industry, the old viruses or old developers very quickly become vastly outnumbered by the incomers. And that's exactly what's happening in our industry. We see exponential growth, colossal demand for developers. And because of this exponential distribution, it's overwhelmingly populated by young folks with lots of energy, but frankly, not much experience. And that's just the nature of it. And what that means is overwhelmingly, the industry is dominated by people who just haven't been through very much. There's another demographic aspect of our industry, which is to do with how we get our education. A very large fraction of us do not have computing science degrees. Who here has a computing science degree? 1, 3, half. Okay, 2.5 out of the 6 people in the room, or 7 people in the room, including me, because I don't have a computing science degree either. So a lot of people get into computing because computers and software are a useful tool, and they find themselves solving problems in whatever other field they were working in, discover they're good at computing, and then maybe decide to make a career of it. And that's pretty much what has happened to me. So a lot of us are essentially kind of self-taught amateurs, or people who've just learned on the job. We've never received any kind of formal training, or still less certification in the industry we work in. A third demographic aspect that I think is really crucial and kind of completes the picture is that our industry has, perhaps more so than ever, incredibly high turnover. And that corresponds to incredibly short tenure at particular jobs, more so on particular projects. There's a lot of churn of people through projects. The residence time of a developer in a particular project is very short. And if you there are different ways to model this or think about it. One way to think about it is of what is the half-life of developers, right? How long does it take for half of your colleagues to move on and do something else and be replaced maybe by other folks coming into a project? And if you look at the numbers, the half-life is about 3.5 years. So every 3.5 years, you can expect half the people you work with to be replaced by, well, if you're lucky and your business is at least stable, to be replaced by other folks. So it's pretty short. And so the institutional memory of a project is very limited, really. And we rely a lot on culture and talking to each other to transmit information down the years, because most successful software lasts a lot longer than 3.5 years. I still have software that I wrote back around the year 2000, 2001 that I know for a fact is still in production and being sold, right? So that was back when I was still writing C++, and it's still out there. So taking these three factors, the kind of exponential growth and the age distribution and the fact we're kind of self-taught amateurs and this very high turnover, what that leads to is the idea that we don't have the collective experience on projects that sticks around for long enough for us to be exposed to the consequences of our decisions. That means we tend not to make good decisions based upon solid engineering principles. And a lot of what we do actually ends up being essentially fashion-driven. So I'm sure many of you have worked in situations where you feel that you're in kind of fashion-driven development. Now, I've used an example on this slide here where, obviously I'm talking about clothing fashion. What does that have to do with software? Well, it's an interesting analogy. The functional requirements for clothing haven't changed for a very long time, right? What are the functional requirements for clothing, right? They're pretty simple. They have to protect us from the elements, right? I mean, you saw the weather yesterday, right? I mean, you don't want to go out that without appropriate clothing. And they need to preserve our modesty, right? They are the basic fundamental requirements of clothing. Yet, even though the functional requirements haven't changed, what we see is that clothing fashion changes continuously. There's a lot of churn. And it's very much the same in the software industry. There's a lot of new things, and a lot of it is essentially not necessarily unnecessary, but you should not adopt it uncritically, right? And I think that's really what this talk is about. It's about, being aware of what's out there and adopting things in a very deliberate way. The talk is called Deliberate Architecture, rather than just adopting things because they're new or, because full style means layers, as it says on the magazine at the front here, right? So maybe that is an architectural statement. Maybe layered architectures will actually be the thing this coming autumn. So we laugh at this, but, and this kind of, I'm not a very fashion affected person. You can probably tell here in my corporate t-shirt, my trainers. And it's easy for us to laugh at the kind of vacuous nature of a lot of this kind of fashion marketing. But actually, when we look at how we market software architectures, it's not really very different from that. It's done in this very visual way. We talk about spaghetti code. We have these little visual depictions which look nothing like any software that I've ever worked on. Right? We have these little microservices that are decoupled. They're floating around. They look like they're in some kind of fluid, like cells almost, right? We have a kind of machine full of gear wheels and chains and cogs and goodness knows what. We have cakes, and in fact, you'll discover that foodstuffs are a repeated motif when it comes to people trying to explain software architectures to each other, and certainly a theme we will return to in this talk. Now, I didn't draw these pictures, right? I didn't decide to depict these different aspects of software as food, but it's a very common thing. This picture is taken from a report from one of the large consultancies. I'm not going to embarrass them by naming them, but they chose to depict microservices as cupcakes, right? I mean, cupcakes are, I'm going to mix my metaphors here, but cupcakes are motherhood and apple pie, right? I mean, nobody objects to cupcakes, right? I mean, cupcakes are just unalloyed good, right? They're just a good thing, right? So, by kind of mapping cupcakes onto microservices, obviously microservices become good. If you were out there just 5 minutes ago or 10 minutes ago, you will have seen trays of donuts that look almost identical to this one, in fact. And I've also seen microservices in reports depicted as donuts. So there's this ongoing theme of food and essentially fashion-driven development. People are advocating things through glossy marketing, right, rather than because of any of the actual engineering qualities that these different things have. Now, the cupcakes and the donuts come from not the same company, but exactly the same kind of company that is responsible for what I'm sure many of you are familiar with, which is the Gartner hype cycle. And so the idea of the hype cycle, well, what can we say about the hype cycle? The first thing we can say is that it isn't a cycle. There you go. So that's an important observation. Yeah.
Is it not a cycle because the minute you've sold somebody something, you have to start all over again? It's a fashion cycle.
Yeah, so I have to repeat your comment because of the microphone here. So the question is it not a cycle? Or the remark is it not a cycle because as soon as we've sold something, we have to start all over again? And once the novelty wears off, right, we have to go around again. I think there's some truth in that. But the basic idea of the hype cycle, for anyone not familiar with it, is that there's some innovation, some invention early on, a technology trigger, maybe something completely new is invented, or more often innovation is about combining things that already exist in new ways. Often these days by startup companies, and then that is hyped up. People are very excited about it because it's new, and we rise up to this peak of inflated expectations. And at this point, everybody gets very excited. There's a kind of gold rush into that area, and people really begin uncritically adopting the technology just because it's new and it's novel, not because it's necessarily a good answer to whatever problem they are working on. Over time, though, as we build experience with the technology, we discover that maybe it's not a good fit in the particular context in which we find ourselves. Maybe worse, maybe it's just a terrible fit in the context in which we find ourselves. I know I've got some good friends here who've recently been involved in following this part of the cycle where I believe they did uncritically adopt a technology because it was new and cool, and they've now discovered that it's really just a terrible fit for what they're trying to do, and now they're having to do very expensive rework to shift onto a different platform. So over time, we slide down into the trough of disillusionment. Often this is referred to as a kind of tech backlash against whatever it is. But then over usually a very extended period of time, years, decades, that collective experience in the industry over where the technology works well is we establish that, we codify it into kind of engineering knowledge, really, a body of knowledge about, well, if you're in this type of situation, this particular type of technology is known to be a good fit for these types of problems, and therefore you're going to have a lower risk outcome if you use it. So it's in spite of the Gartner hype cycle not being a cycle, it's a useful mental model when you're adopting a technology. Just even if you just think about, okay, this technology, where is it in this hype cycle? and you can at least compensate for that. You know, if you think it's around the peak of inflated expectations, then maybe you should just moderate your expectations. Because what you'll notice is out the back of the diagram on the plateau of productivity, then you know, that is not as high as the peak, right? We never get back up to those levels. So, as I warned at the beginning of the presentation, there's one slide in this thing that I made 3 or 4 years ago that's perhaps a little bit out of date, and it's this one. So what I've done is what you can do is you can take any technology, you can draw the hype cycle curve, and you can plot its position on here. So I've just chosen a few random kind of software architectural styles, which we're going to talk about a bit. So things like pipes and filters. I mean, that's a very fundamental software architectural style. You know, we've been using it for decades, very successfully. It's well understood. It's simple. It's easy to reason about. It's successful. It's not in any way fashionable, though, right? But it is out there. Layered architectures, again, well understood. Plugin architectures, again, not something you see too much these days. I'm a huge fan of plugin architectures. Again, well understood qualities. You know, the idea is that we can we can add new behavior to a system only by adding code without having to modify any of the existing code. If you can do that, you have a plugin architecture, right? That's a very powerful quality. Model view controller. That's well understood. That's seen less these days in its original form, but you know, derivative architectures and patterns are used continuously all the time in web development. You know, it gets new iterations of some of these architectures. So many of these things have traveled along this curve more than once. So, you know, MVC started with Smalltalk MVC, and then, you know, 2 decades ago, we had Web Objects MVC, and then we had Ruby on Rails, and, you know, we have whatever we have this year, right? Different things travel along the curve and end up in the same, you know, many of them make it to the end over a course of, you know, 5 or 10 years. Some things do seem to get trapped. Service-oriented architectures, you know, there's a lot of noise around that. My sense of time is a bit distorted post-pandemic, but you know, kind of 15 years ago, I suppose, everybody was wanting to build service-oriented architectures with a, you know, quite large, chunky services and enterprise service buses and those kind of things. Over the last 5 years or so, maybe a bit longer, we've seen a lot of noise around event-sourced architectures, so append-only data stores where we're logging events as things happen. We can replay those events, we can project those events to derive different data from them. Extremely powerful idea, immutable data, very easy to reason about, but a very different way of thinking about building systems from what we were mostly doing previously, which was just mutating data in place. I think what I would say is that some of these things are, because I made this slide a few years ago, some of these things have progressed along the curve now. And I think event sourcing is actually gone through the trough of disillusionment, which I think I detected about 3 years ago, and has begun. And the trough of disillusionment was around the kind of GDPR time, right? People were like, oh my goodness, GDPR, event sourcing, how can those things fit together? Because one of them says we have to just keep everything forever, and the other one says you're not allowed to keep everything forever, right? And there was a lot of confusion around that. You know, people have figured those things out now with time, and we are ascending the slope of enlightenment now. Microservices, I think, is still well up there. A lot of people are still making expensive mistakes pursuing microservice architectures when they really don't need to, and finding themselves doing a lot of busy work, right? I heard another, I'll mention that in a minute, but a lot of these things produce the need to do work which doesn't directly deliver value to anybody. Just keeping the thing running and organizing things can be a lot of work. And, you should question whether you really need these things. I've always been fascinated that service-oriented architectures are trapped in the trough of disillusionment, but microservices, which is also a service-oriented architecture, is at the peak. There's a kind of cognitive dissonance there. Serverless, when I made this slide, was just in the ascendancy. I think that's well up at the peak, perhaps even past the peak now. People are very comfortable with building those things. We're beginning to understand the cases in where they work, where they don't work, where it's appropriate, but there's still huge growth and huge hype and huge, really a lot of growth in new serverless services that are being invented all the time, and more of the software that we used to have to write ourselves is now just available as a service and our job is now to glue those services together, those serverless services together. We can also think about practices, right? I think Agile is well in the trough of disillusionment at the moment for a lot of people. A lot of people in our industry who've only ever been exposed to Scrum, right? That's the only way they've ever worked. Yeah. They've never worked in other ways. They have no exposure to extreme programming or those kind of more engineering-focused practices. And Agile has been taken over by essentially management consultants who don't talk about engineering practices. They just talk about how to organize work, right? Whereas extreme programming was much more engineering-focused. So we really lost something along the way. So I think there's a bit of actually quite substantial Agile backlash going on at the moment. So I would put Agile down in the trough at the moment. I think software architecture as a deliberate activity is also in the trough. I'd like to think it's beginning to emerge. Maybe not. We can separate software architecture practices from software, from having people who are called software architects. We can have developers doing software architecture as well. But I really think the last decade has been a very bad time for software architecture. It's been very much a kind of code first approach to everything, which can and can't work. And then some things have just been kind of complete failures in terms of practices. I think now, nobody's really using UML now. Well, actually, I say nobody. I know people who do, actually, they literally build missiles, right? And that's all done using sysUML and systemML and UML, because their stuff has to work, right? And thank goodness it does. So it's very interesting to think about how the hype cycle, it's a model, right? But I think it's a useful model of how our industry responds to new technologies being introduced and our attitude to those technologies over time. And so, as I said, just being aware of where a technology is on that hype cycle can help you compensate for its position in the hype cycle. So the question then is, well, what causes the hype cycle, right? Why is it like this? Does it have to be like this? Can we stop it being like this? I'm kind of despondent about the prospect of us stopping it being like this, but we could maybe understand why it's like this. And the reason it's like this is because we're human, right? We are not programmed machines that behave in rational ways in the face of some external stimulus, right? We are really just huge bundles of biases, right? And those biases have evolved in us for very good reasons. They keep us alive, right? But they also stop us making good, high-quality decisions sometimes. They're really good decisions for like staying alive or finding food, right? But they're not necessarily really good decisions for building high quality software. So at least being aware of some cognitive biases, again, is one of the ways you can help compensate for some of these effects. So, because I made this slide a little while ago, I've forgotten which ones get highlighted. So I've made some notes here. So I'm not going to go through all of these. I just highlight 4 of them. The first one is availability cascade there, kind of top center. So the availability cascade bias is the bias that says that if you go to a conference like this one and every third talk, so what's a popular thing people are talking about at this conference? I don't know, C++ concepts, right? Or something, right? If you go to a conference and every third talk is about C++ concepts, right? You begin to believe that C++ concepts are a really good idea, right? Whether they are or not for your situation, right? Just the availability of lots of material about that topic makes you think it's good, right? If you go to a conference and all the talks are about microservices, you begin to think they're important and good, whether or not they are in your own context. The other one is the recency effect. So you might have seen this. Well, we don't have music magazines anymore, right? But we used to have these things called magazines, and some of them used to be about music. And, they would have like articles in like best 50 albums ever, right? Remember those kind of things? And you would look through the list of best 50 albums ever, and there was no way they were kind of anyway uniformly distributed over the decades, right? Half of them would be from the last 18 months, right? And that's the recency bias effect, right? It's just people just attach more weight to things that have happened recently, yeah? Same with software solutions, because things are recent, they attach more weight to them. Even if pipes and filters architecture from 40 years ago or 50 years ago is the best solution to your problem, just because it's old, right? You might reject it, or may not be, more likely you just never consider it if you're even aware of it. Another one I'm going to talk about is hyperbolic discounting down there on the bottom left. So hyperbolic discounting is a very technical name, but it means that you discount the long-term effect of decisions you make, right? So most people are exposed to this because most people aren't even if rationally they can think about how compound interest works on your savings, right? You have to think very rationally about that, right? It's much better to put your £100 in invest it and have it compound over 20 years than it is just to go out and spend your money, right? People are terrible at discounting the gains and the costs of things far into the future. And the reason hyperbolic discounting happens is that there are lots of compounding effects, right? I mean, I just talked about interest on money, but lots of things we do in software have compounding effects, right? So that's a big one, hyperbolic discounting. And the last one is a really simple one, is the pro-innovation bias, which is that, just because something is new or interesting, or there's possibly we see it as innovative, then we should do it. Even though because it's new, it's probably very poorly understood. And we are going to be the people who pay the price of understanding it, as well as reap any potential benefits. So we tend to look at we tend to be a very optimistic industry. We tend to always think about the upside risk and not think too much about the downside risk. So where does this leave us as software architects? Well, it's not so fashionable to have software architects now, but people who think about software architecture, enlightened developers, right? People who think about this kind of stuff. And software architecture people are often accused of spending their time drawing boxes and lines, right? And that's a shame, because that's not really what software architecture is about at all. That's just one part of it. It's that, that's just the structure of the software, okay? What are the parts? How do they relate to each other? That's purely structural. For me, what software architecture is really about, or should be about, is about understanding trade-offs and qualities, right? So here are a bunch of software qualities. And these trade off in really complicated, wicked ways, right? And finding your way around these trade-offs is really the job I see as the primary job of people who are engaged in software architecture. So there are some really difficult trade-offs here, right? So I've drawn these. Some of them are kind of naturally opposed to each other. Some of them are not. They're just on the picture because that's where I put them. But for example, performance and maintainability, right? I can write incredibly high performance code, right? But it might be very difficult to read and maintain, right? Because I have to go really low level, or I have to use a much lower level language than I might otherwise be using in the rest of the system in order to get that performance. And so I'm paying for that performance with the maintainability of the code. Now, you come to a C++ conference, and a lot of what's going on here is people trying to come up with ways to write performant code that is also maintainable, right? I mean, that's really the goal, isn't it? Yeah. But these things do trade off against each other. I mean, I spend a lot of my time writing code in much higher level languages these days, but I really pay for that in terms of performance. You know, I write a lot of code in Python, you know, and that is, on a good day, that's 100 times slower than C++, right? So I'm really paying for that. Now, for me, that's a good trade-off. For a lot of the code I write, for other code, it's a terrible trade-off, and I should really use C++. Cost versus reliability, that seems kind of obvious, doesn't it? I mean, you can write unreliable software cheaply, or you can write very reliable software, and it's going to cost you more money to do that. Security and usability, right? Nobody enjoys having to log in or do two-factor authentication on their phone, right? You know, that's not why you're using the software. That's just getting in the way of you as a user achieving whatever goal it is that you set out to achieve, right? You know, nobody wants to do that stuff, but it's necessary to achieve security. So security and usability tend to work against each other. You know, we all need, 20 character passwords these days. You know, it's just a bit of a pain, isn't it? And then you have to switch out into your password manager, and oh my goodness, never get anything done. So lots of difficult trade-offs here. And I think that's really what this talk is about, is approaching trade-offs. Do you want the cake or the apple, right? I love a good apple. I also love a good cake, right? They serve different purposes. They're very different things. They're both food, I suppose, in some sense. But, you have to choose, and you have to choose the right one for the circumstances, right? If you go to a wedding reception and you gave everybody apples, that would not be the greatest wedding reception, right? People want cake in that circumstance, right? So, but if I put one of those cakes in my children's lunchbox to go to school every day, I'm going to probably have my children taken away from me. So you have to, you have to choose appropriate solutions. So really what I want to talk about is deliberate design for software qualities, and to center that as the role of people doing software architecture. So one way to think about deliberate design for software qualities is to think about the forces that act upon a software system. This is well, I mentioned UML earlier, and Grady Booch was very much involved in UML, but the next few slides about thinking about forces acting on software systems is also something that comes from Grady. So some of his ideas have had a longer life than others. He's quite a deep thinker about software architecture topics. So, we have some software system that's represented by the large blue box in the middle here, the system, the solution to our problem. It has a boundary, and there are lots of people or groups of people or other systems which need to interact with that system in some way. They might be people who buy it, the customer. They might be the people who use it, which, in this case, the user and the customer aren't the same, usually, right? In lots of big businesses, the customer and the user are different people. If ever you need a definition of enterprise software, there it is. Enterprise software is software where the customer and the user are distinct people, right? The developers need to relate to the software. They impose a force on the software system. They need to maintain it. Testers need to be able to test it. Managers need to be able to manage its development. Salespeople need to be able to go out and promote it and sell it. Other systems that relate to it impose a force. We can think of them imposing a force on your system. It's a constraint. Your system has to relate to that other thing. If that other system changes, you have to adapt to account for that. So we can think of all these forces acting on the incident forces on the system. And what Grady Booch said is, he said, these forces will resolve to zero, right? And it's a mechanical analogy, but it's a fun mechanical analogy. And the reason they have to resolve to zero is because otherwise your engineered structure, your software, is either going to kind of buckle and collapse and fold in on itself and just implode, right? Or it's going to accelerate to infinity and you're just going to lose it, right? They have to resolve to zero. And so to pursue this analogy a little further, once we have some forces, we can factor these forces into different groups, which I think is a very useful way of thinking about how of the forces that act on systems and what we need to do to take account of those things. So I like to group them into the forces that represent the functions that a system needs to support, the qualities that system has, some principles that we adopt when we're building the system, and constraints which limit what we're able to do. So we'll talk about each one of these. So functions. What is the software for? What is its reason to exist? Right? Why are we building this thing? What use cases does it support? Right? What does it enable to happen in the world that wouldn't happen without it? So features, use cases, functionality. Now, they are obviously the reason for the software you're building to be, right? In a way, though, they're also the least interesting aspect from a software architecture point of view. I'll come back to that. It seems a ridiculous thing to say, but I think it's important, and we will end the talk on that note. Then there are the qualities, and the qualities are, well, okay, given those functions, how well should it do those things, right? So these qualities are often called non-functional requirements, NFRs. That's a kind of unfortunate name because non-functional also means doesn't work, but you have to think of it, it means these are not functional requirements, they are this other thing that we don't have a good name for, right? A good name for them is software qualities, right? What are they? They're things like performance, how fast can you go? Scalability. What's scalability? It's how can I make use of available resources, right? So if I double the amount of hardware resources I have, can I go twice as fast, right? That's scalability. Security, maintainability, usability, fault tolerance. There are hundreds of these. You can go to Wikipedia and look up software quality attributes and you'll get a list of like 200 of these things. The fact that there are 200 of them is what makes this job difficult, right? It's very difficult to even do trade-offs between two things, but when you have to trade off between hundreds of things, it's very challenging. Then we have constraints. These are things that limit our approach. We probably don't have much choice in these. So they are how much money do we have to spend? What's our budget? What does the law say? Right? We can't just go out and build anything. There are legal limits to things we're allowed to do with computers, for good reason. How much time do we have? Right? All software is late, but some software cannot be late. I have some friends who worked on software for the London Olympics, right? You're not going to be late with that, right? It just has to be there, right? They're not going to delay the Olympics while you finish your software, right? You just have to finish it. you know, Y2K type bugs, right? You know, you can't change the date when the millennium changes. You just have to be there, ready. Some of them you have a little bit of flexibility, maybe you don't. How many staff do you have? Who are they? What do they know? Right? All of those things. Can you train them? So they're limitations to what we can do. And then architectural styles. Principles, which are things that they're things we choose to do. They're things that they're like voluntary constraints in a way. They are things that we choose to do to constrain the way we build our software. So we are going to choose a particular architectural style, or we are going to choose a particular programming language, or we are going to have to adhere to particular coding standards, or we are going to do test-driven development, or any of those things. You know, we have some choice. So from a software architecture point of view, for me, the constraints and the qualities are the really major factors that influence the architecture we should choose. So you can think of the functional requirements going into some process that produces software, and the functional requirements manifest as features, right? We build features in our software in order to support use cases, right? Basically. The non-functional requirements go in and they come out as qualities of the software. So non-functional requirements is an input, software quality is an output. Now, what I find fascinating is we treat these things in very different ways in our development processes. So features of software tend to be explicitly captured. You know, so you have a JIRA ticket for that feature, right? They're intentional. We tend not to accidentally implement features, right? Usually I know we all have, but usually it's a deliberate act to implement a feature, right? They're tracked, right? There's some, be it Scrum or anything else, there's some kind of project management process where we know whether that feature is in the queue to be made, we're making it, or we've made it, right? So they're tracked. Moreover, once we've built it, I can go to you and say, where is that feature implemented? And you can say, well, that particular feature is implemented in these 3 files here, right? And it's probably a fairly localized thing in the code, right? It's probably not spread over 3,000 source code files. If it is, you're doing something wrong, but it's probably pretty localized in the code. They're explicitly tested. We've probably written tests of some kind to know whether the feature is working. If this is getting rarer and rarer, but if your system has any documentation for it, it probably documents the features, right? In terms of how to use them, end user documentation, I mean. And features are essentially digital, right? Or binary, insofar as they're either implemented or they're not, right? Half a feature is not much use. Contrast that with the software qualities, very differently handled. They're informally captured, right? If they're captured at all, in terms of thinking about them, maybe you work in an industry that still has requirements documents or a requirements template, right? And it's all about features. There are like 50 pages about features, and at the back in the template, there's this little bit about performance and qualities, right? And somebody's tried to write something because it's a template and they feel they have to write something in there, but it doesn't really make much sense because they were tired by the time they got to that part, and people have just kind of lost interest at the back of the document. So they're very informally captured, and they're often not kind of dealt with numerically. The qualities emerge from the software. Whether you explicitly engineer for these things or not, your software will have these qualities. I'm going to come back to that point. I'm going to come back to this word emergent in a minute. It's a very important word. They're untraceable. If I go to you and say, where is performance? Which source code file is performance implemented in? Right? Doesn't make any sense, does it? Right? It's everywhere. They're cross-cutting. right? Where is usability implemented in your program? Where's usability.cpp, right? It's not there, right? It's because it's cross-cutting. So they're cross-cutting concerns. They're untraceable. They tend to be retroactively redressed. We tend to fall short on the qualities and then have to go back and fix them because the customer says it's hard to use, or the customer says it's slow, or the customer says it doesn't scale, or it's insecure and you don't have any customers anymore, right? We tend to have to fix them afterwards. More and more these days, we monitor these things in production, right? So we deploy the software and then we can monitor how fast it is, how responsive it is. We can even measure usability to some extent. You know, what proportion of users filling their shopping cart on Amazon successfully check out, right? It's very much in our interest as a business to make that 100%, right? If it's 30%, that's maybe telling us something about how difficult the checkout process is or the payment process is, right? You look at companies like Stripe and how successful they have become really just by focusing on streamlining that payment process. They tend to be undocumented and they're generally analog quantities, right? You can have more or less performance, more or less scalability, more or less usability. People have said that features and qualities are orthogonal. I don't buy it. Functionality and quality attributes are orthogonal, it says in Software Architecture and Practice, a famous software architecture book. I don't think they are really orthogonal. I can make your software very secure by taking all the features away, right? For example, that's a trivial example of how they're not orthogonal, but they are, you know, in an ideal sense, you would be able to vary the qualities without changing the features. So ideally, but I really want to come back to this word with respect to qualities about emergent. It's an important word. So where does the word emergent come from? Well, it comes from the philosopher George Henry Lewis, who is not famous. He was basically a failed philosopher. And he's really known for two things. He's known for coining the word emergent, and he's known for being the partner of the author George Eliot. And in all other aspects of philosophy, he is basically sunk without trace. But this is where he, I think this is the sentence where he coins emergence. I'm not going to make you read the whole thing. It's in slightly arcane Victorian prose, but we'll try to extract a bit of it and turn it into something that looks like modern English. And he says, well, with emergent things, with emergence, there is a cooperation of things of unlike kinds. The emergent is unlike its components insofar as it cannot be reduced to their sum or their differences, right? So if we think about some functionality and features in software, if you have one feature, we support one use case, and then you add another feature to support another use case. Now you support two use cases, right? It's just simple additive thing, right? I know it's not entirely that simple, but you understand the argument. However, if you have a bunch of features and you add another feature, what does that do to your usability, right? It's a really complicated function that relates you adding that feature to what happens to your usability or your security or your performance or these other qualities. Those qualities emerge in a very complex way, in a really non-linear way from the functionality. And so I think it's very correct to go back to the original coinage of emergent to use the word to refer to qualities. So software qualities are highly non-linearly related to the code we write. What do we know about non-linear systems? Well, we know that they're really hard to model. It's hard to predict the future of them, what happens. And if we're in the unfortunate position of trying to build a control system around a highly nonlinear system, it's very hard to do well, right? Really tricky. So maybe less so now, but it was very popular a few years ago for almost any conference you went to that involved enterprise software. Maybe it would have happened this week if you'd gone to QCon in London. Somebody would have this slide with this picture of this sapling on it. And the sapling is usually cradled in the nurturing hand of a software architect or something. And very shortly after they used this image, somebody will utter the word emergent in their talk, right? And what I'd like you to do is to consider that when they say the word emergent, you should just mentally translate that to hard to model, harder to predict, and hard to control, right? It's very difficult to have these qualities emerge in a deliberate way from your software. And I think that tells us something about how software is built these days. So to go back to a software system, we most often these days have some kind of agile software development process, which is extremely feature focused, right? We have a queue of features to implement. And, we do those on quite a quick cycle. If you're doing Scrum, you do every 2 weeks, you have a cycle, you have a daily cycle with your stand-ups and all this. And you've probably seen the official Scrum diagram, right? And it's 2 loops. There's the kind of sprint loop and then the daily loop coming off it. And the thing literally looks like a diagram of a pump, right? And that's because Scrum is a feature pump, right? That's what it does. It just pumps features into software on a regular cycle, right? Doesn't often take them out, just pumps them in. Pump. And you can, you see these software systems and they just inflate. It's bigger, 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 bigger. Scrum is a feature pump. But over time, what happens, and crucially, not on the same time scale. Your feature pump is working in hours and days and weeks, right? Over months and years, what happens is that the qualities emerge from the software. And they emerge whether you like it or not, right? Your software is going to have usability, a level of usability, whether you like it or not. It is going to have a level of scalability, whether you like it or not. It is going to have a level of maintainability, whether you like it or not. You don't get to choose whether your system has these qualities, right? They will emerge. You don't get to choose which of the qualities are really important to you either, right? You may become aware quite late in the cycle. And the fundamental problem, which I don't think I'm going to propose one answer to it later in the talk, but the fundamental problem with this is the different time scale between the feature pump and the emergence of qualities. So this kind of, you can, all of the qualities in aggregate, you can think of as a kind of wellness quality, right? Are we in good shape, right? And the difference in wellness between what we have and what we need, delta wellness, right? What happens to that? Well, people complain about the software, right? And what happens to the complaints? They go into Jira as bugs, right? And that delta in wellness ends up encoded in 1,000 defects, right? Saying, well, hang on, your software is too slow on this particular use case. And then there's another unrelated bug over here, apparently unrelated bug on a different use case. But, the root cause is the same, right? It's because some queue somewhere is overflowing and dropping things, right? These things emerge. But because of these timescale differences, what we have is a really brutal low-pass filter on the emergent qualities, right? And if you've worked on any kind of control system, actually anyone who has a shower, particularly anyone who has a shower in Britain, right, has worked with a control system with a really brutal low-pass filter, right, where you turn the temperature control and there's a long delay before the temperature of the water actually changes, right? And then it's too hot and you try to adjust it, and then it's too cold and you have to leap out the shower, right? And then you have to adjust it again and you get back in, right? And that's because there's a time delay, right? And it's very difficult to deal with that. And this time delay effect here happens in software as well. And it makes it, software development looked at like this through this lens, it's a control problem, right? And this is a control problem with a really horrible time delay and a really brutal filter. It makes it very difficult to control. It's basically, in my view, what makes software hard. So what can we do? Well, I think we're very far from having a universal answer from this, even in principle, let alone in practice. But what we can do is try to deliberately design the system so that qualities are likely to emerge, more likely to emerge at the levels we want them to emerge, and less likely to emerge at levels we don't want them to emerge at, right? That is the goal of software architecture, is to get these qualities to emerge at the right levels. So what does software architecture need to do? Well, primarily it needs to facilitate the delivery of the features. We need to come up with an architecture that allows people to build the features that need to be built, because it is the features that deliver the value ultimately, but we need to then deliberately design the system such that qualities are likely to emerge in the right way. I should be careful about quoting war leaders at the moment, but Churchill said it quite well. However beautiful the strategy, you should occasionally look at the results. And as I said before, the reason this is so difficult is there's this fitness landscape of different qualities. And our job is as architects, is to navigate this landscape and find a good solution in the right part of the landscape. The problem is the landscape's invisible. The other problem is it's not a simple two-dimensional landscape like this one. It's like a 96-dimensional or 200-dimensional space. And we're trying to find a habitable zone within that really high-dimensional space where we can build good features and qualities are likely to emerge in the right way. So I am very pro-Agile, I suppose, by many folks' standards. You know, I spend 3 days a week doing ensemble programming. A lot of what we do is test first or TDD. Everything is continuously deployed, value, right? I'm very much into that. At the same time, I think we should recognize the fact that a lot of Agile, as practiced particularly in big corporates, is essentially a feature pump. And software architecture can be a balance to that, to make us think more carefully about how qualities emerge. So, what to do? Well, let's get on to that. So, different implementations of essentially the same thing can exhibit different qualities, right? So this is Twitter on a desktop and Twitter on a phone, right? They basically have the same use cases, right? I can read other people's tweets, I can reply to them, I can retweet them, I can write my own tweets, right? I can follow people, I can unfollow people. You know, there are, I don't know how many use cases Twitter supports, but it's probably less than 50, right? But more than 20, right? It's not a really super complicated product in terms of features, right? It's a very complicated product in terms of software qualities, which is why they need thousands of engineers to make it work, right? But certainly just thinking about the Twitter front end, right? I have the web app and the iOS app, they have high levels of usability. I'm able to perform all these use cases in both platforms. They both need to interoperate with whatever Twitter's using on the back end or talk to the photos library on my phone and all those other things. So there's interop there. Maybe the iOS application is written in Swift. It has high performance. The energy budget on a phone, it's less of an issue these days, but, I can remember where, you were running Twitter and it would just drain your phone, or Facebook would just drain your phone, right? And so energy budget, there's an up and coming software quality for you, particularly if you're working embedded. Whereas on desktop, you don't really care about that. You have more than adequate performance. You don't care about the energy, unless you think about, or maybe about the climate as well. Maybe the web thing's written in some horrendous mess of JavaScript. I don't know that it is, but You can imagine it might be, and it's just a mess, and we have some nice Swift code on the mobile client. But the web application is super deployable, right? Every time somebody visits the page, they could get a new version of the app, right? Whereas the mobile app requires explicit. It's a much more complex deployment process. It has to be reviewed by Apple, maybe. There's a process to go through there. I have to maybe deliberately install it or at least accept the upgrade, right? So arguably it's less deployable. And also portability, right? I can use the web app anywhere, including on my phone, whereas the iOS Twitter app only runs on iOS, right? I can't run it anywhere else. So people have chosen different trade-offs. So really, I'm just saying that functionality is independent of structure, and we can choose, are we going to make a native mobile app or a mobile web application? Those things have different trade-offs, right? Think about those carefully through the lens of software qualities. So to bring this back to, well, how do we solve the problem of predictable emergence of qualities? Well, one answer is to deliberately choose a software architectural style which exhibits known combinations of qualities, right? So think about, rather than saying, oh, I'm going to do microservices because microservices are cool, because I've just been to a conference with 5 microservice talks and my recency bias has kicked in, and obviously that's the thing to do. Think about what qualities your system needs, then look at what software architectures are out there, find out which qualities those architectures exhibit, and then choose the one that has the quality combination of qualities that you need, right? So microservices here, what are the qualities? Well, modifiability is good, right? I can replace a service with another version of that service without having to replace the whole system, right? If I'm doing things well. It's resilient in a way. If a service dies and crashes, I can just restart that service, right? The performance isn't going to be wonderful because straight away I've got a network layer in there. I have all these bits of software which, rather than just passing pointers to each other, is now having to encode things probably into JSON text, send it over the wire and decode it on the other end. We're paying for that. Maintainability might be great, right? Maybe I can choose a different programming language for each service. Deployability is good. I mean, this is the key thing about microservices is independent deployability, right? I can redeploy parts of the application without having to redeploy the whole thing. On the other hand, the operability is maybe quite low. You're going to need a bunch of people whose job is basically to not just get this complicated network of services into production, but keep them there, right? That takes a lot of effort and sophisticated practices and experience, right? So it's easy to point at Netflix and say, well, okay, Netflix do this, it must be right, but Netflix also probably has a bigger budget than you do, so you have to take that into account. Layered monoliths, they have a different combination of qualities. You can see some of them are quite low, which is why maybe some of these architectures are less favored now, right? But they also have some really good qualities, like performance, right? Now we're just passing pointers or references around inside a piece of software, right? That's really quick, instantaneous. Tiered architectures, again, different combination of qualities. So, there are literally books which are essentially catalogs of software architectures, and you can look at them and read about the qualities they have. If you get a book like Software Architecture in Practice, it won't be up to date with microservices and things, but it'll have all the other ones in there. Yeah. So I don't spend an enormous amount of time reading other people's PhD theses, but this one, at least the beginning of it, is worth a read. This is Architectural Styles and the Design of Network-Based Software Architectures. This is Roy Fielding's PhD thesis, and this is where REST and RESTful architectures were first described. And we don't have to read the whole thing. We just have to get as far as page 15. There's a nice quote here. He says, some architectural styles are often portrayed as silver bullet solutions for all forms of software. However, a good designer should select a style that matches the needs of the particular problem being solved, right? The irony is, of course, in web application development, what have we seen happen to REST in the last decade, right? It's just everybody uncritically adopted that for the last 10 years. And now we're beginning to move off that to other things. But there was a lot of adoption there of REST without people really fully understanding what it was all about. And really the term REST and RESTful actually lost its original meaning along the way because of that. To draw an analogy from building architecture, this book, Architecture, Fundamental Issues. I just like this quote from it. Personal stylistic concerns have no place in the work of the professional architect. Again, you should be selecting architectures based upon the requirements, not because of some bias that we're all subjected to. So how is this handled? Well, you probably have some kind of development process that maybe looks something like this. There's a bunch of stuff to do. There's a bunch of stuff you're doing. There's a bunch of stuff that's done, right? On my little cartoon Kanban board here. And the traditional kind of agile response to, well, how do we deal with qualities in software is to say, well, we need to build the qualities into what's called the definition of done, right? So the feature is done, not just when it works, but when it works well, right? When it works without degrading usability, without compromising the security, right? So people try to add the qualities into the definition of done. It's difficult because you might have 20 qualities that you care about. And what happens then, and I've seen this happen several times, is your process then turns into this, because people just add columns to the board, right? For say, well, it's done except it's slow, right? And then it's done except it's insecure, and it's done except whatever, right? It's done except it doesn't work in Chrome, right? So
I'm reminded of the term, it's done, yes, but is it done?
Right, exactly. Is it done? Right, yeah. So while building things into the definition of done is a nice answer in principle, in practice, one of the failure modes I've seen of that idea is this notion that things are never actually done. So I think what's a better idea and more appropriate given how we build and deploy software these days is rather to build these things into the definition of done, is to get them out there quickly and get feedback on them. That's the Agile principle, but then to monitor. Right, more and more now we can monitor these things in production, and we can roll things back if we make particularly egregious mistakes. But generally speaking, we can monitor these, a lot of these things like people successfully completing use cases, or the performance of the system, or how long our deployment pipeline takes to do its thing. Portability, how do you monitor portability? Well, you can't really monitor it, but I think maybe Mac OS is a nice example of this, right? Mac OS started on Mac OS 10, started on PowerPC, right? And then one day, Apple came out and said, well, we're going to move to Intel, right? That wasn't some massive effort at Apple to make sure everything worked on Intel, that they'd always compiled it on Intel, right? I imagine, I've got a lovely new M1 here. I'm sure someone in Apple has been compiling all of macOS on ARM chips for years and years and years, right? So, if you can ensure that your software is portable by putting the work in to do that. I used to work on software that, thank goodness I don't now. I used to write C++ that had to compile on Solaris and IRIX and Linux and Windows, And oh my goodness, right? We had to do that. It's an enormous amount of work. And if you're Apple, you can afford to do it, right? I think it nearly killed me trying to balance all these different broken compilers and find the one form of source code that would successfully go through all of them. Yeah, so. Yeah, I just want to. Yeah, so essentially there are lots of different people who care about your system. They all are going to impose forces on your software, and you need to, as an architect, you need to think rather more broadly about who they are, or maybe they are other systems rather than people, and how those things impinge on your software. I would like to advocate for, even if we don't have dedicated software architects, that's less fashionable now, but people who are responsible for architecture, I would like to advocate that they are really the champion for system qualities, thinking about those qualities deliberately. This talk's called Deliberate Architecture. I'm going to finish on just a piece of advice that I was given by someone I used to work with, who I have enormous respect for. They taught me a lot, and they picked up this advice from somewhere else. And I wish I could trace the original source of it, because then I would cite the source here. But if anybody knows where it comes from, do tell, and I will add it to my slide. But this is advice to software architects. And the advice is this: you look after the quality attributes, and the features will look after themselves, right? You've probably heard the phrase, you look after the pennies, the pounds will look after themselves. That's the same idea. And what this is saying is, you have to think about it, because of course we can't forget about features. But what it's saying is there are so many other people in your organization who are thinking about features, right? Developers actually are mostly thinking about features, right? Most of the time. That's fine. Project managers are almost certainly thinking about features. Testers are thinking about features. Your customers are thinking about features, right? Everybody is thinking about features. Nobody is thinking about qualities until it's too late, because they emerge, right? So you as a software architect or person responsible for the architecture, if you think about the qualities, right, you're not going to end up in a situation where the features aren't being implemented. There are plenty of people around you who are going to make sure that happens. All you have to do is make sure that the software system, the architecture you put in place, facilitates them doing that, and just let them get on with it. You think about the qualities of the system that you want to emerge. So I think it's excellent advice. It's difficult to follow, like all advice in practice, because you're going to get dragged into doing features or thinking about specific things. But it's worked very well for me. I have a small consultancy now, so I'm not doing architecture on big projects, but I have been the lead software architect on in fairly large companies with hundreds of developers, and this advice has worked very well for me. It's never been my problem that we have not been shipping features, right? It's always been my problem that the thing is slow or unmaintainable or buggy or doesn't scale or isn't portable to whatever. So I'm going to end on that piece of advice there. Thank you very much for listening.